December 16th, 1944, Belgium. The dawn broke slow and gray over the frozen hills. Snow hung thick on pine branches, and every breath of wind carried the faint metallic echo of distant guns. German infantry from the 18th Volksgrenadier Division crouched in their foxholes, waiting for the Americans to reply to their morning advance. They had fought through mud, through fire, through every kind of shelling the Western Front could throw at them. Artillery was predictable, the whistle, the impact, the delay. But that morning something changed. The first explosions didn't strike the ground. They bloomed above it, sharp, blinding flashes suspended in the mist, raining steel fragments that cut through the air like invisible saws. Helmets clattered, shouts echoed. Men threw themselves into the snow. There was no warning whistle, no crater, no mercy. The sky itself had turned into a weapon. When the silence finally returned, the white forest was shredded with smoke and shattered bark. Survivors whispered that the Americans had found a way to command the air, to make their shells think. What they faced that morning wasn't magic. It was science, a tiny metal brain no larger than a hand, born in American laboratories thousands of miles away. By the winter of 1940, the world's armies still fought with technology born in the last war. Artillery was the king of battle, but it ruled by brute force, not precision. Each shell depended on a fuse that determined when it would explode, contact, time, or command. None were truly reliable. A contact fuse could only detonate on impact, devastating if it struck a tank or bunker, useless if it buried itself in mud. The timed fuse was worse. It depended on guesswork. Gunners calculated how long their shell would fly, twisted a dial with gloved hands, and hoped the clockwork inside would match their mathematics. A second too early or too late meant nothing but wasted steel. By 1941, in North Africa, the British Army learned this the hard way. German dive bombers descended faster than their anti-aircraft shells could predict. Thousands of rounds exploded harmlessly behind their targets. Air defense was a gamble, and every miss cost men and morale. In Washington, a quiet realization began to take shape. The problem wasn't firepower. It was intelligence. The Allies had the guns, the shells, the factories. What they lacked was a fuse smart enough to know when it was near a target. That idea that a shell could think was almost heresy in 1940. Electronics were enormous, fragile, and power-hungry. Radios filled desks, not bullets. But the concept reached the Office of Scientific Research and Development, OSRD, the civilian body created by President Roosevelt and led by an electrical engineer named Vannevar Bush. Bush had seen how the British were struggling under German air raids, and he understood the stakes. He gathered a small group of physicists, engineers, and mathematicians and gave them a mission that sounded impossible. Create a fuse that could sense its target and detonate itself, automatically in flight. It would become one of the most complex and secret projects of the war. By 1942, a small laboratory under Johns Hopkins University in Maryland was founded specifically for this purpose. The Applied Physics Laboratory, or APL. The men who worked there were not soldiers. They were scientists, inventors, and radio engineers, many of them barely out of graduate school. They worked in sealed rooms filled with oscilloscopes and spare parts from radio factories. Their task was to fit an entire radar set, a transmitter, receiver, and power source, inside the nose of a 5-inch artillery shell. It had to survive 20,000 times the force of gravity at launch. It had to detect a moving aircraft and trigger itself within a few meters, and it had to do it reliably hundreds of times. The engineers called it the variable time fuse, or VT fuse. The press would later know it as the proximity fuse. Early prototypes failed spectacularly. Circuits shattered under acceleration, batteries froze, vacuum tubes cracked. Yet progress came slowly, stubbornly. The key was in miniaturization, the same principle that would one day drive computers. RCA and Western Electric began crafting impossibly small vacuum tubes, each one the size of a fingertip. By late 1942, a working prototype existed. When fired from a test gun, it sent a signal that bounced off a target and returned milliseconds later. The moment that echo reached a specific strength, the shell exploded. It was the birth of the world's first smart weapon. Still, secrecy was absolute. Even within the U.S. military, few were told how it worked. The fuse was labeled restricted, and early production was limited to naval anti-aircraft guns. On the decks of Pacific destroyers and cruisers, gunners watched in awe as Japanese planes disintegrated under precise airbursts. The idea that a fuse, not a gun, not a shell, but a fuse, could change the balance of war was becoming reality. And yet, few outside those ships knew of it. To the soldiers in Europe still loading conventional shells into their howitzers, the proximity fuse remained a rumor, a whisper of technology that might one day save their lives. The men in the Ardennes, crouched in the snow 4 years later, would learn exactly how real it was. The fuse's leap from bench to battlefield was not an accident. It was a deliberate, secret race, a marriage of academic physics and American industry pressed into wartime tempo. By 1943, the Applied Physics Laboratory had solved the core problem. A tiny radio transmitter and receiver could be tuned to detect the echo from a nearby target and trigger detonation. But solving the physics was only half the fight. The other half was production, making millions of fuses that would work under combat conditions. The War Production Board and the Ordnance Department turned to private industry. Radio firms and instrument shops across the country were pressed into service. RCA and other contractors manufactured the small vacuum tubes and components. Small machine shops produced shell noses and precision casings. Battery makers developed compact power cells that could survive extreme acceleration. The assembly lines were like watchmakers' benches scaled to the size of artillery inventories. Each component had to meet impossible tolerances. Security was total. The fuse was given the highest wartime restriction. Drawings were compartmentalized. Engineers signed non-disclosure oaths. Shipments moved under armed escort. Even Allied officers were kept in the dark for months. The American military feared two things: that failure in the field would expose the secret, and that premature knowledge would let the enemy copy it. The logic was cold and simple: preserve the fuse's advantage until it could be produced in overwhelming numbers. The first operational home for the VT fuse was the sea. Navy gunners fitted proximity fuses into 5-inch and 3-inch anti-aircraft shells and began firing them at Japanese aircraft in 1943. From the decks of destroyers and cruisers, sailors watched spectra of explosions bloom around incoming planes, airbursts that shredded wings and sent pilots into the sea. Reports from the Pacific described dramatic improvements in hit rates and a sharp drop in effective raids against task forces. The fuse had transformed a ship's thin sky of flak into a lethal curtain. That success carried consequences. The Army and its artillery chiefs watched those at-sea accounts with hunger and caution. There was debate in Washington. Some military leaders argued for immediate, wide distribution to anti-aircraft and field artillery units. Others feared that using the fuse over European soil would let German scientists recover fragments and reverse engineer the technology. The compromise was cautious. The fuse would be used at sea and in limited ground operations where the risk of capture was low. As production ramped, controlled land trials followed. In late 1943 and through 1944, more fuses flowed to the Pacific and to anti-aircraft defenses in Europe. Crews who had trained with timed and percussion fuses began to learn a new grammar of gunnery. Instead of lobbing shells and waiting, they could fire into a funnel of space above a formation and watch the air itself answer. Ammunition expenditure fell while lethality rose. The fuse reduced the need for saturation barrages. A single, precisely timed airburst could stop an enemy strafing run or shatter the soft top of an armored vehicle. Word of the fuse did not travel quietly. Rumors reached German technical battalions and frontline commanders. Shells that exploded without hitting the ground. Aircraft shredded by unseen bursts. Increased effectiveness against low-flying attackers. German intelligence collected fragments and interrogated prisoners, but documentation remained scarce. The Americans had been careful to scatter the parts and keep their methods classified. For a time, the Germans called it mysterious airburst shells in their reports, a phrase that carried equal parts fear and bafflement. By the autumn of 1944, production finally met demand. Millions of fuses had been manufactured in dozens of plants. The Ordnance Department authorized broader use. The time came when the technology could no longer be hoarded at sea alone. The fuze moved inland in sufficient quantities to be issued to field artillery units preparing for the winter campaigns. That deployment set the stage for the fuze's true test. When the first massed VT fuse barges fell over European battlefields, the effect would not simply be measured in tonnage. It would be measured in shock, of infantry who had never seen the sky itself explode, of enemy artillerymen who could not reconcile their maps and timing with the sudden, unseen detonations above their heads. The fuze's story was no longer only one of invention and industry. It was becoming a story of people, of gunners learning a new skill, of commanders rewriting tactics, and of opponents forced to ask how to fight something they could not easily see. Those human reactions would shape doctrine and morale. They would also force desperate attempts at replication. But before those attempts could bear fruit, the fuze had to be used where it could change a battle's course. On a cold morning in a field artillery park, a sergeant named Carl checked a crate stamped with the ordnance mark. Inside were 5-inch shells with noses unlike any he'd seen. Smooth, precise, and labeled with black bands. Men at the battery had trained for hours on range tables and fuse timing. Their hands knew the weight of a shell and the feel of a faultless primer. This was different. The fuze removed some of the old rituals. It demanded new trust. Training changed quickly. Crews learned to think not in seconds, but in volumes of sky. Instead of dialing a timed fuse and drawing a straight fire lane, a forward observer would call coordinates while the gunner set elevation for a burst above a formation. The fuze did the arithmetic. The gun captain could now order barrages that detonated at a calculated height, forming a curtain of shrapnel where an enemy column would pass. Ammunition that once needed saturation could now achieve effects with far fewer rounds. The human impact was immediate. Artillerymen reported a new kind of precision that felt almost personal. A lieutenant in the 30th Infantry Division would later write that a single battery, using VT-fused shells, stopped a German counterattack that had swept through 2 miles of hedgerow. The account was clinical on paper. Rounds fired, enemy casualties, positions held. But the men remembered shock and relief. Shock at the sudden airbursts, relief that fewer rounds and less waiting had bought them time and lives. Commanders adapted tactics. Brigade and division staffs began to integrate proximity bursts into defensive plans. Fields once left open for armored advance could be denied by lethal overhead barrages. Combined arms teams used the fuze to protect infantry against counterattacks, and to defend bridges and supply points from low-level air attack. Mortar and howitzer crews worked with fighter controllers to create overlapping envelopes of lethal airburst coverage. Logistics changed too. The reduction in required rounds eased supply pressures. A single well-placed VT barrages could replace an extended barrage that had previously chewed through truckloads of ammunition. For units advancing over narrow roads and bridges, the lighter ammunition footprint meant mobility, shorter resupply lines, fewer vulnerable convoys. The fuze, in this sense, became not only a weapon but a multiplier of sustainment. Morale shifted in subtle ways. Soldiers who had endured endless preparatory fires and seen the waste of German counter-battery tactics began to trust artillery again as a protective force rather than an indiscriminate hammer. That trust was doubled in crews who now watched enemy aircraft disintegrate in precise bursts or infantry assaults halted by overhead detonations. The psychological weight of artillery, once a source of dread for both friend and foe, gained a new reputation as a guardian. Yet adoption was not without friction. Some traditionalists mistrusted a device that took timing out of human hands. Others worried about the fuze's reliability in mud and cold. Commanders debated doctrine, when to use proximity fuses and when not to risk fragments falling into enemy hands. There were rules and restrictions that accompanied each crate issued. Use in the open, avoid urban concentrations when possible, and never fire a proximity-fused shell into terrain where fragments might be recovered intact. For those gunners facing German counterattacks in late 1944, the fuze offered a pragmatic kind of heroism. It converted trained skill into decisive outcomes with less waste and more certainty. Those moments of gunners loading shells, of officers watching the sky bloom with airbursts, of infantrymen standing in stunned silence after an overhead curtain stopped bayonets and armor alike. These were human scenes that changed doctrine forever. Across the enemy lines, however, confusion grew. Reports filtered back of shells exploding midair with no visible pattern. Artillery officers scratched notes in margins, trying to reconcile clocks and maps with sudden, overhead detonations. The human reaction on the German side: astonishment, fear, a scrambling attempt to explain the phenomenon, would become the subject of technical obsession and attempted countermeasures. On the German side of the line, artillery officers prided themselves on method. They trusted calculation, the geometry of fire, the reliability of mechanical time fuses honed since the Great War. But by late 1944, as US and British guns began firing shells that burst midair with unnatural consistency, their mathematics started to fail. The first official reports reached the Heereswaffenamt, the German Army Weapons Office, in November. Field units along the Ruhr River and in the Eifel sector described unexplained air detonations. Observers noted no muzzle flash anomalies, no delay mechanisms. A colonel from the 18th Volksgrenadier Division wrote, "Shells now detonate at uniform altitude above advancing troops. Defensive trenches offer little protection." At first, the Wehrmacht's technical staff suspected faulty Allied fusing or defective shells that burst prematurely. But when similar detonations appeared across separated fronts, the coincidence was impossible to ignore. Intelligence sections tried to collect fragments. Teams combed craters, searching for fuse remnants that could reveal a secret. Most were mangled beyond recognition. What fragments survived showed traces of glass, copper, and fine wiring, materials foreign to known Allied munitions. Some analysts proposed an electronic or magnetic trigger. Others dismissed it as superstition. Yet reports kept arriving from the field, airbursts accurate to 10 meters. Infantry losses severe despite cover. In captured American documents, German scientists finally encountered a coded term, VT. It appeared without definition, but its context suggested proximity or variable timing. The term became a riddle. Radio engineers at Peenemünde speculated that the Americans had somehow miniaturized radar circuits. The idea was met with skepticism. Everyone in the room knew how large a radar set was. Towers, valves, power supplies. Impossible, one said. Not in a shell. But the evidence grew undeniable. Luftwaffe crews reported anti-aircraft fire over France and the Netherlands that seemed preternaturally accurate. Bombers flying low to evade radar found themselves intercepted by sudden rings of explosions perfectly aligned with their altitude. One pilot's debrief recorded his disbelief. "It followed us down. Every burst at our wing height, every time." Technically, the Germans were capable of conceptualizing such a device. Their own scientists had experimented with radio-based detonation during the 1930s, but they lacked the miniaturization and industrial capacity to make it work. German vacuum tubes remained too fragile, too large. Their electronics industry was fragmented by bombing and scarcity of materials. Where the United States could call upon entire corporations to standardize a design, Germany could only rely on isolated workshops. Emotionally, the shock ran deeper than technical envy. Artillery officers who had built careers mastering timing tables suddenly found their own doctrine obsolete. Veteran gunners spoke of a feeling of helplessness, that the sky itself, once neutral, now favored the enemy. Soldiers in trenches along the Ardennes learned to fear still air as much as visible shells. They knew that even unseen rounds could burst above them. Attempts to respond were pragmatic but futile. Orders were issued to dig deeper positions, to construct overhead cover, to disperse formations more widely. Counter-battery efforts intensified, hoping to destroy American guns before they could fire. None of it reversed the imbalance. Even the vaunted German heavy artillery, with its precision optics and range-finding instruments, could not offset the advantage of a shell that no longer depended on guesswork. The technological realization came too late. By the time German research institutes confirmed that the fuse likely used miniature radio waves, Allied troops were already fielding it in numbers that overwhelmed any hope of interception or replication. What German scientists could only sketch on paper, American assembly lines produced by the millions. For the first time in the war, German reports described U.S. artillery not as predictable or ponderous, but as superior in every respect. And in the frozen forests of Belgium, where fog and snow blurred every horizon, that superiority was about to prove decisive. December 16, 1944, the Ardennes offensive begins. At 5:30, the stillness of the Belgian forest shattered under the thunder of 1,600 German artillery pieces. In the gray half-light, shells rained on American lines stretching from Monschau to Bastogne. The Wehrmacht's final gamble, Wacht am Rhein, had begun. Within hours, German armor and infantry surged through the fog, striking the unprepared 99th and 106th Infantry Divisions. For the U.S. Army, the first days were chaos. Communications faltered, weather grounded Allied aircraft, and German panzer divisions clawed deep into the Ardennes. Towns like St. Vith and Malmedy became desperate choke points. The Americans fell back under heavy pressure, until the guns began to speak differently. At first, the German troops didn't understand what had changed. Their experience told them how artillery behaved: predictable, sequential, survivable if they timed their movements between barrages. But when the 2nd Armored and 30th Infantry Divisions were ordered to hold key sectors near Malmedy and Stavelot, the Americans unpacked something new from their ammunition trains. Crates marked VT, proximity-fused shells. The authorization had come from the top. General Eisenhower and his artillery chief, Major General Everett Hughes, had agreed that secrecy no longer outweighed necessity. The fuse would finally be used on European soil. If it failed, so be it, but if it worked, it might stop the German advance. At dawn on December 24th, the first major VT-fused barrage began. Across the snow-covered ridges, batteries of 105 mm and 155 mm howitzers opened fire. The rounds didn't bury themselves in the frozen earth. They detonated above it, precisely at head height. The effect was immediate and terrible. German infantry advancing through tree lines suddenly found themselves under a canopy of explosions. The air seemed to ignite. Each burst shredded everything below in a cone of steel fragments. Cover that once protected them, foxholes, ditches, shallow trenches, became death traps. Soldiers ran, but the sky followed them. Observers described the phenomenon with awe. The airbursts formed a continuous, rippling wall of fire that moved in perfect rhythm with advancing or retreating troops. Where ordinary artillery forced men to the ground, proximity-fused fire forced them to freeze in fear or flee outright. It changed the geometry of combat. Reports from the front were staggering. A single battalion's barrage near Stavelot halted an entire German regiment's assault in minutes. The 30th Infantry Division, badly outnumbered, held its lines despite multiple counterattacks. Artillerymen could now engage moving columns with unmatched lethality, no longer guessing the perfect moment of detonation, but letting the fuse decide it. Within hours, word spread across command posts. The fuse worked, better than anyone had imagined. German advances that had gained ground for a week began to slow. Infantry refused to move through open areas. Commanders reported confusion and panic among their men. For American soldiers who had endured days of retreat and cold, the change felt almost supernatural. The same snow and fog that had hidden the enemy now hid their defense. A silent field of invisible sentinels bursting at will. Eisenhower later remarked privately that the VT fuse was the most important new development in field artillery since the shell itself. Others called it a miracle of science. To the men in the Ardennes, it was simpler, the weapon that turned desperation into defense. And as Christmas approached, the fuse's power would be tested one final time, when American guns switched from holding the line to driving the enemy back. December 25th to 28th, 1944, Bastogne, Belgium. Snow fell in thick silence over the encircled town. Inside the frozen perimeter, the men of the 101st Airborne Division dug deeper into the ice. Ammunition was low, rations thin, and medical supplies nearly gone. Every road was cut off. German loudspeakers called for surrender, but Brigadier General Anthony McAuliffe's answer, "Nuts!" echoed defiance through the ranks. Outside Bastogne, the American artillery battalions supporting the trapped paratroopers faced their own grim reality. Each shell had to count. Then, from the supply convoys fighting through the snow, new crates arrived, VT-fused ammunition, marked for immediate use. The order came straight from General McAuliffe's staff. Use them all. At 1600 hours on December 26th, as German infantry massed near Marvy for a renewed assault, the American guns opened fire. 105 mm howitzers barked in perfect sequence, their shells cutting through the gray sky. German officers urged their men forward through the snowdrifts, convinced they could reach the American foxholes before dusk. Then, halfway across the open field, the air above them erupted. The proximity fuses worked flawlessly, detonating at 10 to 15 feet above the ground. In seconds, the white field was clouded with black bursts and razor-sharp fragments. German observers later reported it as a storm of invisible blades. Soldiers who dropped to the snow for cover found no safety. The explosions hung over them, scything downward. The attack collapsed within minutes. Survivors staggered back toward the tree line, disoriented and broken. When the shelling lifted, American gunners could hear no organized response, only the low wind over the battlefield. The proximity fuse had made its European debut in full measure. That night, an American forward observer near Hemrel sent a coded message back to headquarters. Airburst effect unbelievable. Troops advancing against us simply disappeared. The word spread through the command net like electricity. Battery commanders, long accustomed to guesswork and delay fuses, now had something precise, responsive, and terrifying. Every incoming German formation became a grid to be erased. By December 28th, when Patton's Third Army finally broke through to relieve Bastogne, the battlefront had transformed. Wherever proximity-fused artillery supported American lines, German attacks faltered. Their advance had reached its peak and began to collapse under a rain of invisible precision. Captured German field reports later told the same story. At the 26th Volksgrenadier Division's command post, officers tried to analyze the new weapon. They measured shell fragments, timed detonations, and even attempted to dig up unexploded rounds. But the fuse's secret, its tiny radar transmitter, was beyond their comprehension. The enemy artillery now fires with impossible accuracy, one officer wrote. It is as if the shells know where we stand. The psychological effect was as devastating as the physical one. Veteran soldiers who had survived Stalingrad and Normandy began to doubt their training. They moved under cover only at night. Even the rumor of automatic airburst artillery caused panic in reserve formations. On January 3, 1945, when the weather finally cleared and Allied bombers returned to the skies, the German counteroffensive was spent. The fuse had done its quiet work, unseen, unfelt until the instant it struck. What had begun as Hitler's desperate winter gamble ended in retreat and ruin. For American gunners, the message was clear. The weapon had saved lives, held the line, and turned the tide. For German commanders, it was worse. An invisible enemy that no amount of courage or camouflage could defeat. The U.S. Army had fused science with fire, and in doing so, changed the nature of artillery forever. January 1945, Western Front. The snow still blanketed Belgium, but the front had shifted. German columns that had once thundered westward now crawled east, broken, leaderless, starving. The Ardennes offensive had cost Hitler over 100,000 men, dead, wounded, or captured. The Allies had bled heavily too, but they had held. And in that bitter winter, something had become clear to every commander from Eisenhower down to the newest gun crew. The American artillery had not just survived the offensive, it had transformed it. At First Army headquarters, staff officers began reviewing fire reports from December. The data shocked even the veterans. Barges using the VT proximity fuse achieved kill rates nearly double those of time fuses, and their effectiveness in poor weather far exceeded expectations. Fog, snow, and night, traditional shields for infantry, were now meaningless. The U.S. Army's artillery had become all-weather, all-conditions death from above. A classified post-action report from the 30th Infantry Division summed it up in a single line. Without the VT fuse, we could not have held our position. The results spread through the branches of command faster than any formal directive. Corps artillery officers requested more fuses by the thousands. General Bradley authorized expanded use across the entire Western Front. Factories back in the United States, from Crosley in Cincinnati to Eastman Kodak in Rochester, began working around the clock. The miracle fuse, once top secret, was now a frontline necessity. But while American gunners celebrated, German analysts were in disbelief. At OKW, Oberkommando der Wehrmacht, headquarters, captured U.S. shells were rushed to laboratories for inspection. Metallurgists cut them open, dissected every layer, only to find nothing they recognized. The miniature radio transmitter inside the fuse was years ahead of any German equivalent. Reports to General Jodl described it with reluctant awe. The enemy employs a small radar device within each shell, detonating at precise distance. This technology is beyond our present means of manufacture. The implications were enormous. It wasn't just a better fuse, it was a signal of what the Reich could no longer match. The United States had fused industry and invention into a weapon that combined radar, electronics, and mass production. Something Nazi Germany, starved of resources and bombed into fragments, could never replicate. In field hospitals and command posts, German officers spoke bitterly of the shell that sees. Infantrymen whispered that the Americans had machines in the sky. The proximity fuse became a symbol of technological inevitability, the moment the balance of science had permanently tipped westward. Meanwhile, Allied headquarters realized what they had unleashed. The British, who had jointly developed the concept, immediately pressed for more units for anti-aircraft defense over the Channel. The Americans, flush with success in Europe, began shipping fuses to the Pacific, where they would soon rewrite another chapter of the war. Back in Washington, the National Defense Research Committee compiled final performance summaries. One line in their report carried a quiet pride. The VT fuse increased the effectiveness of artillery fire by a factor of 4, perhaps the greatest single improvement in fire control since the invention of gunpowder. But to the soldiers who had lived through Bastogne, St. Vith, and Malmedy, it wasn't about numbers. It was about survival. The fuse had taken the guesswork out of death, and given them precision in a war defined by chaos. And as news of its Pacific deployment reached Europe in early 1945, a new realization dawned. The fuse that saved Bastogne might soon decide the fate of Japan. March 1945, Manila Bay, the Philippines. American warships entered the harbor under a canopy of smoke. The Japanese Navy was finished as a fighting force, but kamikaze aircraft still struck daily. The U.S. Navy had faced a new kind of terror. Pilots who would not retreat, who turned their aircraft into bombs. Anti-aircraft fire, once the fleet's best defense, had struggled to stop them in time. Then came the order from Washington. Proximity-fused ammunition was cleared for naval use. Within weeks, every major U.S. cruiser and destroyer in the Pacific carried the new fuses. The results were immediate. Where gunners once needed hundreds of shells to hit a single diving plane, they now needed a fraction. A proximity-fused 5-inch shell could detonate within meters of its target, shredding wings and engines with precision unseen before. The sky, once ruled by suicide tactics, became an American killing ground. Japanese pilots were the first to realize the change. Approaching task forces in late spring, they found themselves dying before reaching attack range. Planes simply vanished into clouds of timed explosions. By the Battle of Okinawa, Japanese commanders described the Allied anti-aircraft screens as walls of fire. Over 7,000 kamikaze sorties were launched. Barely 1 in 10 reached their targets. In internal Allied assessments, the proximity fuse was credited with saving thousands of sailors and preventing catastrophic damage to invasion fleets. Admiral Raymond Spruance noted in his post-battle report, "Without the new fuse, our losses to suicide planes would have been unendurable." For the Japanese high command, the realization came too late. Their radar systems could not match American miniaturization, and their industry lacked the capacity for such delicate electronics. Even attempts to replicate captured fragments led nowhere. By summer 1945, Japan faced the same problem Germany had faced in the snow, an enemy whose science outpaced strategy. The proximity fuse's reach extended beyond defense. When the U.S. Army prepared the final air raids over Japan, VT-fused shells were issued to anti-aircraft units protecting B-29 bases on Tinian and Saipan. They guarded the bombers that carried out the most destructive missions of the war, including the atomic strikes. In a sense, the fuse became a silent guardian of the aircraft that ended the conflict. After Japan's surrender, Allied engineers analyzed the full data set. Across both theaters, proximity-fused shells accounted for unprecedented accuracy in ground, naval, and air defense operations. In total, over 22 million fuses had been produced by American industry, each one a tiny triumph of science and logistics. Historians later viewed the proximity fuse as part of a technological trinity with radar and the atomic bomb. While the bomb ended the war, the fuse had decided it long before. It had transformed artillery into a precision instrument, denied the enemy air dominance, and proved that electronic warfare had begun not with computers, but with a small pulse of radio energy inside a shell. In post-war Europe, German engineers examined captured VT rounds in Allied demonstrations. Some reportedly applauded after witnessing an airburst detonate perfectly at 25 feet above target. The emotion was not admiration, it was resignation. They knew their defeat had been sealed not only by numbers, but by innovation. The proximity fuse marked the moment when warfare crossed into a new age, one where victory depended not only on courage, but on the microscopic perfection of circuits and signals. In the Great Chronicle of World War II, the proximity fuse is often overshadowed, hidden behind the thunder of tanks, the flight of bombers, and the blinding light of the atomic age. Yet its legacy runs quietly through every battlefield it touched. It was not a weapon of destruction alone. It was a weapon of precision, born from intellect and necessity. When it first arrived on the front lines of Europe, soldiers saw only a small metal cylinder. Few understood that inside it pulsed one of the earliest battlefield computers, a miniature radar set that could sense the world around it and act faster than any human calculation. It was the first true union of science and combat, the invisible hand that changed the way men fought, lived, and survived. For the Germans, it was an invisible adversary, silent, unseen, impossible to counter. For American gunners, it was hope in the snow, proof that ingenuity could hold the line when courage alone was not enough. And for history, it marked a turning point, when the power of ideas became deadlier than the power of armies. After the war, many of its inventors, scientists from Bell Labs, MIT, and the British Admiralty, moved quietly into the new fields of radar, missile guidance, and spaceflight. The proximity fuse had opened a door that would never close again. Every modern weapon that thinks, reacts, and senses, from smart munitions to guided rockets, traces its lineage back to that tiny fuse. A device so small, yet so decisive, that it made even the most disciplined enemy kneel before the precision of American science. The fuse didn't just redefine artillery. It redefined war itself.